Scenario: a 0.5 kilogram block is placed initially on top of a vertical spring with a spring constant of 200 Newton meter at position A. After a few seconds, the block moves down 2.5 centimeters down to position B. Then, a few seconds later, moves an additional 7.5 centimeters down to position C. Consider the system to be the block, spring, and earth. Question: calculate the change in the spring's potential energy from position A to position B. The answer: the spring potential energy US at A is defined by 1 half kx squared. K is the spring constant and x is its displacement away from equilibrium. Notice the x here is equal to 0 because the spring is at equilibrium. There was no displacement. So it's still at 0 joules. It moved down to 2.5 centimeters. So you can write it 1 half kx squared as the equation for the spring potential at point B. But when I plug it in, please note that this is in meters, but it was given in centimeters. The reason why it has to be in meters is because the spring constant was in meters. So make sure you convert it correctly. So once you plug it in, you should get 0.0625 joules of energy. That is how much it has at point B. So if you want to know the change, it goes from 0 joules to 0.625 joules. That would be the change in the spring's potential energy. There was a gain in the spring potential energy because there is more of the compression of the spring. Next question. Without calculating, explain whether point C will have less, equal, or the same amount of spring potential energy as position B. The spring potential energy is defined by the compression distance. Notice from position B to position C, there was more distance being displaced for equilibrium. So, it will actually have more potential energy because the displacement from equilibrium is greater. The total would be about 9 point, no, it would be 10 centimeters in total away from equilibrium at position C. Okay, it has more energy because there is a larger displacement away from equilibrium.